So I'm going to talk about using enhanced computation to get good revenue bounds in multidimensional setting. This is work by Alon, Michal, Feldman, Ophir, Friedler, Inbal, Talgam-Cohen, and Matt Weinberg. So in the marriage between mechanical design and computer science, one of the main agendas is to deal with complex resource allocation problems. And complexity can arise in both the items might not be homogeneous and the valuation of the bidders might be complex. And there are indeed many real life examples of this kind of complexities. So once we get into complex settings, we still know how to maximize welfare. There is a closed form of how to do it. We just run VCG. But if we want to maximize revenue, we get into much more trouble. And the optimal mechanism in complex settings is known only for a handful of such settings, such as maybe an additive bio with two items distributed identically and so on. But if you want something more general, we don't know how to characterize the optimal mechanism. Some very specific tailored special cases for which we can characterize the optimal mechanism, but otherwise we quickly run into many barriers. And in computer science, there are usually two common solutions for complexities. One is to give some approximation, for instance, give some approximately optimal mechanism, and this has been a very fruitful line of research recently. And another path we can go is to give ourselves an advantage, to add more resources, and then we can tackle the optimum. And in our talk, most resources will be more bidders, and the mechanism we'll use is just a VCG mechanism. Okay, so let's, we said that multi-dimensional setting are complex, so let's start with a single item. This is pretty well known. And if we want to maximize welfare, then we can just run a second price auction. We don't need no distributional knowledge, nothing. But if we want to maximize revenue, then now we have to have some distributional assumption. And Milestone gives us the recipe how to do it. And I stress again that we need to know the distribution in order to maximize revenue. But a really elegant solution for this problem was offered by Bulow-Klemperer, which said that we can either try to find out what's the underlying distribution, or just add another bidder, run the VCG mechanism, the second price auction, which is prior independent. We don't need to know the prior, and get more revenue than the optimal revenue maximization mechanism. And I stress that this holds, and our results as well hold if we assume regularity. So we'll assume regularity of the distributions throughout this talk. And this result is very robust because we don't need to learn the distribution. This distribution can even change like at times, and we still are guaranteed to get more revenue. And also, second price auction is arguably a pretty simple mechanism to run. Okay. So let's move to a multi-dimensional setting. Instead of an orange, we might have a strawberry and a banana. And we assume that the bidders' values are sampled from the same product distribution. So the distributions for the different items might be different, but they are sampled from the same product distribution independently of each other. And we assume that they are additive across the values are additive across the items they get. So the value for a bundle of items is just the sum of the values of the items. And when we move to multi-dimensional setting, we quickly run into barriers. For instance, the optimal mechanism might be randomized. It might be hard to compute what is the optimal mechanism. And only recently, some approximations were found to the optimal mechanism. So we have two choices. Either we can run something that is randomized. We can't compute it, actually. And we might have, the buyer might have infinitely many options to choose from. And we also need to know the priors, or we can just add some more bidders and run VCG. And we take the second path and try to explore what happens in this direction. Okay, so we're also going to talk about a bit about additive values subject to feasibility constraint. That means that each bidder has a set of feasible sets of items that you can get, and the value for a set of items is the value for the best feasible set of items. So for instance, if we have, if we have these 3 items, and the feasible sets are the strawberry and the banana or the singleton, then if we get the bundle, the best feasible set is the strawberry and the banana, and the value is the sum of the values of the best feasible set. Okay, so in order to describe our result, we coined the term computation complexity, which roughly means how many bidders do we need to add to the original environment in order for VCG, for running VCG with this additional number of bidders, to get more revenue than the optimal mechanism without this additional number of bidders. Okay, so let me repeat it. We look for the number, x, that if we run VCG with x additional bidders to the initial n bidders that we have, then we get more revenue than the optimal mechanism with the original n bidders. And to have some feeling about this term, about this terminology, we'll know that we already discussed that the computation complexity of a single item auction is 1. We just need to add another bidder and run VCG, and we get more than the optimal mechanism. Okay, so let's sum up our results in a table. So let's assume we have n is the number of bidders and m is the number of items. So if the valuation is additive, then if we add an additional n plus 2m minus 1 bidders and run with VCG, and this is in addition to the original n bidders, then we get more revenue than the optimal mechanism with the original n bidders. If we look at the feasibility constraints, for instance, you can think about unit demand bidders. All bidders are unit demand. Then we need to add another m minus 1 to get more than the optimal mechanism. And actually, we noticed that our techniques give us even something stronger, that the feasibility constraint might be different across bidders. The valuations, like the distribution of the values, are identical, but some bidders might be unit demand, some might be additive, some might want 2 items, and still we can bound the number of bidders we need to add, which might also have different feasibility constraints. And we have some refined result from Metroid, which depend on a parameter rho, which I won't have time to get into. And I just want to state that we can't have like a nice constants like in the single item case, because some parallel walks and prior walks show some impossibilities, which are more than constant. For instance, we need to have something like the number of items in some cases. Okay. So these are some related works. I won't get into them in detail, but I just managed there are some work on Bulow-Klemperer type theorem for multidimensional settings, but they attack the deterministic and dominant strategy setting, and we tackle the randomized and BIC setting, and as Yao showed, we might need to tackle the BIC setting. There are some other prior independent works, so our work is prior independent. We don't need to know the prior. And there are some other works that deal with not knowing the distribution as well. Okay. So let me just give you some taste of the techniques. Just a simple case where we have a single additive bidder. So we have a single additive bidder and want to ask the question, how many bidders do we need to add so that run VCG will give us more than the optimal revenue? And the proof will be similar to the simple proof of the Bulow-Klemperer theorem, and will involve 3 steps. One is to give some upper bound on the optimal revenue. The second step will be to come up with some auction, which gives us more revenue than the upper bound in step 1. And the third step will be to show that VCG beats the mechanism can in step 2. And if we change these 3 steps together, we can see that VCG gets more than the upper bound of the optimal revenue, which is the desired result. Okay. So, and we'll start even with a simpler example. Well, there is a single bidder, and the items themselves are sampled from an identical distribution. Okay, so for the upper bound on the optimal revenue, we use a new duality framework of Tsai, Devanur, and Weinberg. And this is the upper one. Let me try to give you some intuition of this. So a trivial upper bound on the revenue is the expected welfare. We can get more than the welfare. But this is too loose. We can't achieve this. If we have an equal revenue distribution, we can get this as revenue, the welfare. So what they noticed that if we take the item with the highest value and truncate its value to the positive portion of the virtual value, then this is still an upper bound of the revenue, and this is attainable in some cases. This is a pretty good upper bound. So the upper bound would be to take the favorite item, the item with the highest value, and consider the virtual value, the positive portion. And for all other items, consider the value. Okay. Okay, so the second step will be to come up with a mechanism that gets more than the upper bound 1. But we notice that run VCG on additive bidders, they actually run a second price on each item simultaneously. So we also separate the benchmark to each item's contribution. And the mechanism that we come up with will cover the item J's contribution to the optimal revenue. So we come up with a single parameter mechanism that covers item J's contribution to optimal revenue, which is this term. Okay? And the mechanism is follows. So now we add n-1 bidders. We need to add additional bidders. And we run a second price auction with lazy reserve. What does it mean? We see who has the highest value. And if this highest valued bidder is also above the reserve, is allocated. Otherwise, nobody is allocated. And he pays appropriately. So what are the lazy reserve we'll use? For item J, we use a lazy reserve to ensure its virtual value is non-negative. And for all other bidders, we won't have any reserve. And there are two possible outcomes for this mechanism. Either item agent J in this mechanism has the highest value, and then it gets the item only if his virtual value is non-negative. So, and we count the revenue, his revenue as his expected virtual welfare. These are equal. So in this case, we get this term. So if the agent J has the highest value, then we get the positive portion of the virtual value. And the other case is that there is some other agent with a higher value. And in this case, he pays at least he pays the second highest value, which is higher than agent J's value, because he didn't win. Okay. And in this case, we get this term. So this mechanism covers the item J's contribution to the expected revenue. And the third step is to show that VCG beats this mechanism, which is actually showing that second price auction beats this single parameter mechanism for item J. And this is just three simple steps. The first is we gave you some, I showed you some single parameter mechanism. Of course, the revenue is less than the optimal mechanism, a single parameter mechanism. And now we apply the Bulow-Klemperer theorem to show to say that if we had an additional bidder to the n-1 bidder we already added, then the revenue of the second price auction is greater than the mechanism that upper bounds the benchmark. And combining this together gives us that the computation complexity of a single additive bidder is at most m, which means that if we have m bidders and run VCG, then we are good. Okay, so what's the problem of extending this to item distribution which is not identical? The problem is that we cannot couple the event that agent J wins with the event that item J has the highest value. This happens with different probability. And to fix that, we noticed that the duality framework of Tsai et al. Actually gives us this benchmark as well, which means that we don't truncate the value of the highest item, but the item with the lowest quantile, which means the item that if we sample from the distribution, it's less likely to be above it than all other items. And now we can notice that fj of vj is just uniform 0,1, so the probability of item j to be the highest quantile item is just 1 over m, which is exactly the probability of agent j to be the highest valued agent. And the proof follows as I showed you. Therefore, we can also show that the computation complexity of a single additive bidder with different item distribution is also at most m. Okay, And let me just talk a bit about how we extend it to feasibility constraint. So so this is some sort of reduction. So let's assume we show that the computation complexity of a additive setting of n additive bidders is C, which means that the revenue of running VCG with additional C bidders is greater than the optimal revenue of the original n bidders. Then this inequality follows quite easily. What is this inequality? We say that now if we restrict the feasibility constraint of the bidders, we get less revenue. And this is because every mechanism that is feasible for feasibility constraint bidders is also feasible for bidders without constraint. We can assume without loss of generality that the optimal mechanism allocates only feasible sets of items. So we actually have a larger outcome space of octants to choose from, so the revenue just increases when we move from constraint bidders to unconstrained bidders. And if we show this inequality, which means that if we compare VCG for additive bidders with VCG with down closed bidders with additional n-1 bidders, then we get more revenue for down closed setting. Then if we look at the two endpoints of the inequalities, we get that if we add C minus M plus n-1 bidders and run VCG, then we get more than the optimal revenue of the original setting. And this gives us that the computation complexity is also bounded by C plus n-1. So actually, this is exactly the main technical challenge. And I won't go into this. So this is too technical for this talk. But you can ask me afterwards. I'll be happy to answer questions about it. And some open questions we have. Some are already worked on by Ophir, Michal, and Aviad, which is to get some tighter bounds on the computation complexity, some trade-off. Maybe we want some approximation and we want to add less bidders and so on. And we also might want to look beyond additive subject to down close constraints. There are sub-modular valuations. There are more complex evaluations to choose from. And maybe running VCG is not the best parallel-independent mechanism to run. Maybe some other parallel-independent mechanism give us more revenue. So these are all good questions. And that's it. So thank you.